This is an addendum to the series of lectures titled Making Sense of QFT. I got a feedback on my lectures, and people say that they're somewhat dry and abstract. Some questions remain unanswered, and it would be a good idea to practice with exercises. So, here you go. In this tutorial, which goes in parallel with lecture 2 about Wigner's particles, I am going to answer some frequently asked questions, and we will solve together a few exercises. Here is the plan. Question 1. What is the physical meaning of irreducible representations of the Poincare group? Question 2. What is the physical meaning of reducible representations of the Poincare group? What is the physical meaning of Casimir operators? And how come that electron's wave function has two components, but Dirac's field has four components? In exercise 1, we will prove a very important operator relationship which will be used frequently throughout this course. Exercise 2. How do components of momentum transform under rotations? In exercise 3, we will show that energy momentum form components of a relativistic 4-vector. Next, show that mass squared is a Casimir operator. And finally, we'll build the Hilbert space of a massive spinless representation of the Poincare group. What is the physical meaning of irreducible representations of the Poincare group? First, let me remind you that when we build a representation of a group, we first select a Hilbert space, and then for each group element, we choose a representative unitary operator or matrix in this Hilbert space, in such a way that products of these matrices repeat the products of elements in the group. Let me now mention a useful theorem which states that a unitary representation of any group is irreducible if and only if it is cyclic. What is the meaning of a cyclic representation? Suppose that we took any vector psi from the representation Hilbert space and applied to this vector the matrices representing all group elements. In the figure, I show these images by green arrows. Next, we took a linear span or all possible linear combinations of all these vectors. And if in the result we obtain the entire Hilbert space H, then our representation is cyclic by definition. And according to the quoted theorem, it is irreducible. In other words, a representation is cyclic and irreducible if by starting from any vector and applying all group elements to this vector, we can explore all corners of the Hilbert space. The other possibility is that our vectors, blue and green, and their linear combination will occupy only a portion of the full Hilbert space. There will be other portions or subspaces which could not be reached by applying representation matrices to the vector psi. In this case, we'll say that the representation is not reducible, is not irreducible. It will be called a reducible representation. Let me now demonstrate this idea of a cyclic representation on the example of a massive spinless particle. As we discussed earlier, states of this particle can be described by momentum space wave functions, or equivalently by wave functions specified on the mass hyperboloid. Here I showed one such wave function that is localized near momentum value 0. The observer moving to the left with velocity v will ascribe a different wave function to the same particle. The new wave function is obtained from the old one by application of the boost operator. Apparently, the new wave function will be localized around a non-zero value of momentum. For observer moving to the right, the particle momentum will be negative. Then it seems plausible that by applying to our original state all kinds of Poincaré transformations, including boosts, rotations, and translations, we will be able to explore the entire mass hyperboloid. This means that no corners of the Hilbert space will be left untouched. Therefore, this representation is cyclic and irreducible. Similar considerations apply to particles with spin 1/2. In addition to momentum, the states of such particles are distinguished by their spin, which can take values 1/2 and -1/2. We can also say that instead of one mass hyperboloid, wave functions are now defined on two equal mass hyperboloids, one for spin up states and another one for spin down states. If we choose the initial wave functions on the spin up hyperboloid and apply to it all possible boosts, then, as we described earlier, we'll be able to explore the spin up portion of the Hilbert space. But we can also rotate the observer by 180 degrees, which will open for us the spin down hyperboloid. By doing that, we again will be able to reach all corners of the Hilbert space, thus proving that the spin 1/2 representation is cyclic and irreducible. Question 2. What is the physical meaning of reducible representations of the Poincaré group? In the previous question, we explained how irreducible representations work. Now it's time to see how reducible representations are different. There are many physical systems which are described by reducible representations of the Poincaré group. Actually, all systems that are not elementary particles belong to this class. For example, the Hilbert space of any multiparticle bound state, such as the hydrogen atom, is a space of a reducible representation. In this drawing, I showed the energy momentum spectrum of the hydrogen atom. In fact, only 3 of its low energy states. In textbooks on non-relativistic quantum mechanics, the energy spectrum is usually shown as a set of energy values. But this is only justified if we have our atom in the state of zero total momentum. But the total momentum can take any values. For example, from the point of view of a moving observer. A larger momentum is accompanied by a larger total energy. This means that in a full description, atomic energy eigenstates form so-called mass hyperboloids. Each such hyperboloid has a definite value of mass. Here I showed three such hyperboloids. Mass m0 corresponds to the ground state of the atom. Mass m1 is the first excited state, and mass m2 is the second excited state. Now, suppose that for the observer at rest, the atom was in its ground state, and its wave function was localized in the neighborhood of zero total momentum. This wave function is shown by the red broken line. The wave function is non-zero only on the ground state hyperboloid. Wave functions of the same state from the point of view of observers moving to the left or to the right are shown by full red lines. These wave functions are also localized on the ground state hyperboloid. Because by changing the point of view, it's not possible to excite the atom. Thus, we conclude that functions on each mass hyperboloid form a subspace of the total Hilbert space. In each of these subspaces, some irreducible representation of the Poincare group acts, and the full Hilbert space is reducible because it is represented as a direct sum of irreducible hyperboloid subspaces. The full representation of the Poincare group acting in the Hilbert space of the atom is a direct sum of irreducible representations. We may also note that each mass eigenstate of the atom behaves as if it was an elementary particle. But the name elementary particle is reserved for very specific objects, so mass eigenstates of multiparticle system would be more appropriately called elementary systems. We have discussed classification of states by eigenvalues of just one Casimir operator, the mass. This classification could be also extended to eigenvalues of the second Casimir operator, spin squared, but we will not do it here. The same ideas can be expressed in the language of linear algebra. If representation is reducible, then there exists a Hilbert space basis in which representation matrices for all group elements have the same block diagonal form shown here. In particular, this means that if the state vector has non-zero components only in the green subspace, then under action of all group elements, the state vector will never leave this ground state irreducible subspace. So this representation is definitely not cyclic and definitely not irreducible. What is the physical meaning of Casimir operators? We already know that Casimirs, by definition, are operators commuting with all 10 generators of the Poincare group. The Poincare group has only two Casimir operators, mass squared and spin squared. Of course, any function of these two operators also commutes with all Poincare generators, but m squared and s squared are the only two independent Casimirs. Zero commutators with generators means that Casimirs remain invariant under all inertial transformations. This means that if one observer measured certain values of mass and spin in a physical system, then all other observers would agree on these values. In other words, mass and spin are true intrinsic observer-independent properties of physical systems. Later we will learn about other intrinsic properties like charge and flavor, but they are not related to space and time symmetries. They have to do with the way systems interact with each other. How come that electron's wave function has two components, but Dirac's field has four components? Electron's wave function and electron-positron Dirac field are two completely different physical and mathematical objects. They have very little in common. Perhaps the only similarity is that for some inexplicable reason, many people keep using the same Greek letter psi to denote these two different quantities. I don't want to go deeper into this subject now. Let us return to it later when we'll discuss the idea of quantum fields. Now I would like to switch to exercises. First, we'll prove this simple operator identity. It is very useful and we will meet it frequently throughout our course, especially when the number t is purely imaginary. Then the exponent of tb is a unitary operator and the exponent of minus tb is the inverse unitary operator. Then the left-hand side is how observable A changes with respect to inertial transformation represented in the Hilbert space by unitary operators. Here is my plan for the proof. First, I'll check that both sides of this identity satisfy the same differential equation. T derivative of operator is equal to the commutator of this operator with B. And the second step is to show that both sides have the same initial condition at t equal to 0. Let's first take the t derivative of the left-hand side. It is a sum of two terms. In the first term, we take the derivative of the left exponential factor. In the second term, derivative of the right factor. Derivatives of exponents are simple. They are in the parentheses. And in the next step, we simply rearrange the parentheses and realize that we achieved the desired goal. The t derivative of the original product, shown in blue, in parentheses, is equal to the commutator of this product with operator B. Next, we take the t derivative of the right-hand side and obtain an infinite series, which is exactly the same as commutator of B with the original series. So the required differential equation is satisfied indeed. Next, check the initial conditions. At t equals 0, the left-hand side is equal to A. And the right-hand side is equal to A2. Thus, we prove that both sides of this identity satisfy the same differential equation with the same initial condition. So these are identical functions of t. Exercise 2. How do components of the momentum operator transform under rotations? We will simplify the problem and instead of the general case, we consider how the x component of momentum transforms under rotations about the z-axis. We know that the generator of these rotations is the total angular momentum component Jz. In the Heisenberg representation of quantum mechanics, the operator px prime in the rotated reference frame is obtained by sandwiching the original operator px between unitary operator of rotation and its inverse. Here the formula proved in the last exercise comes in handy. So replacing operator A in this formula with px and B with Jz times the rotation angle phi divided by h bar, we get the infinite series of commutators. The required commutators can be taken from our basic list of Poincaré-Lie algebra relationships. Epsilon ijk here is a so-called Levi-Civita symbol. Therefore, we get explicitly the two required commutators. Next, I substitute these commutators in the original series. And notice that all terms are proportional either to px or to py, and collect the sums of factors in two parentheses. Finally, I notice that the sums in the parentheses are exactly the well-known Taylor series for trigonometric functions cosine and sine. This proves that the x component of momentum transforms as x projection of a 3 vector. Similar calculations can be done for other components as well. Next exercise. Show that energy momentum form components of a relativistic 4 vector. Here by energy momentum I mean a 4 component quantity which consists of the total energy operator h and 3 components of the total momentum multiplied by the speed of light c. I introduce the factor c for two reasons. First, c times momentum has a dimensionality of energy, thus all components of my 4 vector have the same dimensionality. Second, formulas become a little bit simpler in this notation. We already know that under rotations the momentum part transforms as a 3 vector. The energy is invariant under rotations because operators h and g commute. Now we will focus on boost transformations. In particular, we'll choose the boost along the x-axis whose generator is operator kx. We have to apply the unitary exponent of this generator to all components of our 4 vector. Transformations of the py and pz components are trivial because kx commutes with these operators. To calculate transformations of h and px, we'll have to turn to Lie algebra commutators shown here. In particular, we'll need these two commutators. First, consider transformation of energy. Substituting the above commutators into our standard formula, we'll see that the series has only two types of terms, those proportional to h and those proportional to px. Collecting the factors together, we can notice that they are Taylor series for the hyperbolic cosine and hyperbolic sine. A similar calculation performed with the x component of momentum also results in hyperbolic trigonometric factors. Next, I'm going to show that these hyperbolic trigonometric expressions are actually equivalent to more familiar Lorentz transformation formulas. Keep in mind the definition of the rapidity theta. The hyperbolic tangent of theta is equal to the ratio v over c. Then it's easy to show that hyperbolic cosine and sine are given by usual relativistic square roots. Substituting these square roots into our transformation formulas, we obtain the usual Lorentz relationships of special relativity. Show that the total mass squared is a Casimir operator. I'll remind that m squared is basically h squared minus p squared. We actually have to prove that m squared commutes with all 10 generators of the Poincaré-Lie algebra. Let's begin with generators of translations. These 4 generators commute with each other, and with m squared is a function of them. Therefore, m squared commutes with both total momentum and total energy. Next, check rotations. Generators of rotations commute with energy. We also know that momentum is a 3 vector. So the square of momentum is a 3 scalar which commutes with rotations. This proves that m squared commutes with rotation generators. A bit more efforts are needed to prove the commutator of m squared with boost generators. Instead of direct calculation of these commutators, we are going to prove an equivalent result that m squared remains invariant under finite boosts. I like this method because it will allow me to use results of the previous exercise. So I'm going to apply a finite boost transformation to h squared minus p squared times c squared. Obviously, this is equivalent to using transformed h and p in the usual formula for the m squared. Now we substitute here formulas for h theta and p theta obtained in the previous exercise. Expand the brackets and reorder terms. Then use the basic property of hyperbolic trigonometric functions. Cosine squared of theta minus sine squared of theta is equal to 1. And obtain the original formula for m squared. This proves the desired commutator. In the last exercise, we'll construct the Hilbert space of a massive spinless representation of the Poincaré group. Please note that among Poincaré algebra generators, there are 4 mutually commuting operators, px, py, pz, and h. According to basic quantum mechanics, in our Hilbert space, we can build an orthonormal basis of common eigenvectors of these 4 operators. Let us mark these eigenvectors with eigenvalues px, py, and pz. We omit the eigenvalue h because the operator of energy is not independent. We know that in each irreducible Hilbert space, the operator of mass is just a number m. Therefore, h is a function of mass and 3 momentum eigenvalues. In irreducible space with zero spin, the three components of momentum label all basis vectors without degeneracy. But in irreducible Hilbert spaces of non-zero spin, for complete labeling we'll have to use also one component of spin, but we will not discuss this possibility here. Any state vector in the Hilbert space of a massive spinless particle can be expressed as a linear combination of the basis vectors labeled px, py, pz. Therefore, all such vectors are describable by momentum space wave functions. To complete the description of this representation of the Poincare group, we'll have to determine how these wave functions transform under actions of various transformations from the Poincare group. We discussed this point in our lecture. Thank you.